Hello and welcome to the section 2.4 lecture today for Bridges Math Probability. Today we're going to be looking at some other ways that we can combine probabilities. And so I want to start with this, make sure this is working here. Okay. I want to start with this look at a Venn diagram and how that relates to, how that can relate to probability and figure some things out. So let's just go ahead and get started here. The first thing I want to do is to describe in words what each one of these numbers means. Now, as I did in class, I'll do the same here. 100 is actually a tough one to start with. So what I'm going to do is I'm going to start with the 15. Now, a lot of people would say that the 15 is the number of juniors. And that's close, but those are the juniors that don't own a vehicle. Okay, because that 15 doesn't include the 5 that do own a vehicle, not to give that part away, but the 5 would be the number of juniors that own a vehicle. Okay, then bouncing around a little bit to kind of keep the same pattern going, the 50 right here is kind of the same idea. It's the number of seniors that don't own a vehicle. And the 30 would be the seniors that do own a vehicle. The 20 is kind of a hard one to figure out. But if we notice, it's in the vehicle owner circle, but it's not in the junior circle and it's not in the senior circle. So that's the group that own a vehicle. But we're going to say not juniors. And not seniors. Okay. So that, they might be sophomores, they might be freshmen, they might be super seniors and just don't classify themselves as seniors. There's a lot of options there, but the important part is that they don't fit into the junior or senior category. And then the 100 would be, look at it how you want to, not juniors, not seniors, and don't own a vehicle. Okay, they kind of don't fit into any of the groups that we have. Now I've started using shorthand later on these. And I've used J for juniors, V for owning a vehicle, S for seniors, and the 100 I've just classified as N, kind of none of the above. And so we're going to use that shorthand to not have to write so much. Okay, let's go ahead and look at what we have. Sorry, this is the first time I'm recording a video with my new tablet. That's also why I'm not really looking right at you while I do it, but yeah, it's kind of working out. So what's the probability of a randomly selected student being a junior? So we're looking for a probability that someone's a junior. And for that, we want to look at all the ones that are juniors. So the juniors constitute 15 and 5, 20 of the entire sample space. Now we do want to know how many people are in that total. So we've got 20 there, 40 there, 70 there, 120 there, and 220 total. So I do need to know that there's 220 total. We'll need that quite a bit. Okay. So the probability that someone was a junior, we said was 20 out of 220. Now if we reduce that, an easy way to reduce it is to drop the zeros and then figure out what we have. We have 2 out of 22 or 1 out of 11. And the next one, the probability of owning a vehicle is going to be how many people own a vehicle. It's not just the 20. It's the 20, the 30, and the 5. So that's going to be 55 out of 220. And if we reduce that, they're both multiples of 55 actually. And it's going to turn into 1/4. Okay. Last one we have is probability of being a senior. Now there's 80 seniors out of our 220 total. Seniors, 220 total. And that's 8 over 22, which is going to turn into 4 out of 11. So now we start seeing the shorthand being used a little bit more. And I'm going to kind of use the numbers that I have up here so I don't have to scroll up and back and all that. The probability of being a junior or a senior. There were 20 juniors and 80 seniors, so there's 100 total of those two. Over 220 would turn into 10 over 22, which looks like 5/11ths. The probability of owning a vehicle or nothing is the 55 vehicle owners and the 100 non-vehicle, non-junior, non-seniors. And we get 155 over 220. Which will reduce to about 31 over 44. The last one of these or statements, juniors or vehicle owners. There were 20 juniors, there were 55 vehicle owners, but that's a little bit off. Let's go ahead and double check that on the sheet there. If I look at what I just said, and there were 20 juniors and 55 vehicle owners. I've actually double counted this 5. Okay, that 5 made it into both groups, and so it's a little bit, or it's double counted. So what I really want to look at is the 15 plus the 5 plus the 20 plus the 30. And that's 50 and 20, which is 70. So 70 out of 220, which would reduce to 7 over 22. And the important thing there, not 75 over 22. Okay, now I'm looking for some AND probabilities. And when we're dealing with AND probabilities, what we talked about before is that we multiply. And technically, what we just did when we look at OR probabilities, we want to add. But with AND probabilities, you can either multiply or you can look at the intersections. So vehicle owners and seniors, there's 30 of those. And so this is just 30 out of 220. Which would reduce to 3 over 22. Probability of juniors and seniors. Again, if we look for their intersection, their overlap, juniors and seniors don't overlap. kind of makes sense because it's pretty hard to be a junior and a senior at the same time. So the probability of being a junior and a senior is 0. Think about that and make sure you understand why that's the case. On the last one here, the probability of being a junior and a vehicle owner, there were only 5 of those out of my 220. I can divide them both by 5 and I'm going to get 1 over 44. Okay, now in this we came up with a couple that were special. We talked last time about independent and dependent. And those came up when we had and scenarios. So it kind of happens in these two. And what we said is if things are independent, then the probability of A and B was equal to the probability of A times the probability of B. And encourage you to look at those two and scenarios that worked out, not so much this one because there was no overlap, and see which one fits into that category. I'm not going to do that, but if it fits into that category, if this formula works out, then they're independent. If that formula doesn't work, then they're dependent. And that's as easy as that definition is. We also found, and we didn't talk about them, but we found what we call inclusive and exclusive events. Exclusive events are events with no common outcome. And inclusive events are events that can happen at the same time. Okay. And we do get different probabilities when we are dealing with those. And I want to look at, we've got one that's inclusive and one that's exclusive up above. And there's probably more than one of a couple of them, but I want to take a look at the ones that I've already dealt with. When I look here at the probability of being a junior or a senior, this 5 over 11 actually comes from the 1 over 11 and the 4 over 11. And it comes from adding those two together. And these are called exclusive events because they don't have a common outcome. Juniors and seniors have no overlap. And so the probability of exclusive events, if we have A or B, is just equal to the sum of those probabilities. Okay. The ones that are inclusive events, and so this one was exclusive because there was not an overlap between those two. And sometimes you'll hear that called mutually exclusive, and that's just saying that the two of them, when we just look at the two of them, they don't share any common outcomes. Okay. The other one is inclusive, and we kind of saw that happen in this one here when we kind of counted, if we looked at we looked at the probability of J and the probability of V, and that was these two. And we tried to add them. We tried to say, well, there were 20 juniors and 55 vehicle owners. Then we realized, well, the 5 of those are counted twice. The 5 juniors that owned a vehicle were counted twice. And so what we really have to do, if we're given a situation like that, is we still want to add, because we're dealing with OR, so we still want to add the probabilities, but we want to get rid of the double counted, at least one of the rounds of the double counted area. That double counted area is the AND probability. So we want to subtract the probability of A and B. We're not taking it out, we're taking out its repeated instance. Okay, we had that there twice, and so we want to get it off of there the second time. Let's look at a way that we can combine all these ideas into one visual that can help us figure these out. So I'm going to reuse a lot of the definitions that we've had already. Independent events are events that don't affect each other. And dependent events are events that affect each other. Sorry, it seems like even with my new little drawing tablet here, we still get that lag with the pen. The formulas for these, if they're independent, then we have the probability of A and B as the probability of A times the probability of B. And then if they do affect each other,
please go to Mr. Henderson,
we have A and B.
Jeremiah Trevino, please go to Mr. Henderson's room 26 at this time.
Sorry about that. Probability of A and then the probability of B given that A happens. So if we know that A happens, and we're going to, if they're dependent, we're going to say the probability of B given that A is something that's going to happen. Okay. Some examples that we used here. For independent, we said something like flipping a coin twice. And for dependent, we said something like drawing 2 cards. And I made sure to say, I'm not going to write it here, but without putting them back. Yeah, without putting the cards back. So that's independent and dependent. When it comes to our OR events, we had exclusive and inclusive. So let's go ahead and figure out those, reuse those same definitions. Exclusive events with no common outcome. Sorry. Inclusive events are events that happen at the same time. I need to say that can happen at the same time because Because it's not guaranteed that they're going to happen at the same time, but if we can say that that they could, then they're inclusive. Formula for these. Again, we're dealing with OR situations. So this one would be probability of A plus the probability of B. This one a little bit more complicated. My pen's falling further behind. We said probability of A plus probability of B, and then minus the probability of the overlap. So some examples of exclusive, we said being a junior. Or a senior. Inclusive, we said being a junior or a vehicle owner. Okay. Sorry, but I need to use the shorthand there. If you want to write those out, that probably wouldn't be a bad call. Let's go ahead and look at a couple examples here. We want to determine whether the events are inclusive or exclusive, and using our best judgment here. Kind of going with, I know that we usually say like, well, yeah, it could happen, so that means it's inclusive. Let's not overkill ourselves by trying to make everything inclusive. Okay, taking Algebra 1 and Algebra 2 is not that realistic. We would say that those are exclusive, because I've had students take Algebra 2 and Geometry at the same time, but not Algebra 1 and Algebra 2. Running and sleeping, I don't see that happening very often, even though, of course, I had somebody say, well, what if you are sleepwalking and you start running? Probably not going to happen. What if you're running a 100-meter dash and then fall asleep? I don't see that happen very often. Let's be a little bit realistic here. Taking Algebra 1 physics, I would say most freshmen do that, so that would be inclusive. Drawing a face card in a club. Well, there are face cards that are clubs, so that's also inclusive. Okay, so that's the notes for today. Go ahead and give those practice problems a shot. Let me know if you have any questions. Otherwise, I hope you have a great day, and we'll see you in